Fluid and electrolyte fluxes in the gut. The gut is a large epithelial interface between the external environment and the milieu intérieur. Considerable quantities of fluid and electrolytes from the extracellular fluid pass across the mucosa into the gut lumen and are reabsorbed. Thus, the digestive tract consists of organs of conservation as well as assimilation. And it is in the light of this that order and disorder in fluid absorption can best be understood. A complete definition of fluid and electrolyte transport in the digestive tract is as yet not possible because progress is hampered by the inaccessibility of the lumen, by varying geometry, and by the intermingling of absorptive and secretory tissues. Factors regulating the passage of fluid and solutes across the membranes and the special conditions imposed by the structure and function of the intestinal mucosa are discussed in the first half of this review. Then, following a survey of the specialized methodology of research as applied to man, the integrated processes of absorption and secretion and their derangements in disease are reviewed. This is Fluid and Electrolyte Fluxes in the Gut by Sidney F. Phillips, M.D. and David L. Wingate, M.B. Department of Medicine, Gastroenterology Unit, Mayo Clinic, Rochester, Minnesota, and Department of Gastroenterology, London Medical College, London, England, published in 1979, called Advances in Internal Medicine, Volume 24. Basic structure and function of membranes. Permeability, aqueous, and lipid. It is generally agreed that the essential component of cell membranes is a phospholipid bilayer that incorporates proteins and is enveloped in them. Thus, transport across biologic membranes is concerned with the transfer of water and water-soluble or lipid-soluble solutes through a layer that is essentially lipid and therefore hydrophobic in nature. Solutes that are soluble in lipids readily permeate cell membranes. Water and aqueous solutes, in contrast, are insoluble in lipids and therefore unable to permeate the membrane by the same mechanism. However, water and aqueous solutes do penetrate lipid biologic membranes, and it follows that these barriers cannot be completely impermeable to the aqueous phase. The simplest treatment of the permeation of lipid membranes by water and aqueous solutes is the assumption that membranes are porous with aqueous channels crossing the membrane. The need for this biophysical approach to intestinal transport arose from the work of Vischer and his associates, who showed that the unidirectional fluxes of water across the intestinal mucosa proceeded in both directions, bidirectional fluxes, and that the net water movement, net flux, represented only the difference between the bidirectional fluxes. The simplest model for explaining the bidirectional flux of water and aqueous solutes is the pore membrane. If pores exist, their dimension should be a rate-limiting factor in aqueous permeation. Permeation will also vary with the molecular size of the solute. Such models have proven to be operationally useful by studies in the intestine with solutes of different molecular size, showing that the rate of permeation decreases with increasing molecular size. An average pore diameter has been computed for different regions of the human gut. Physiologically, molecular size is not the sole determinant of permeability. Electrolytes are ionized, in which case permeability depends on the size of the hydrated ion. A further factor is the charge carried by the ion. Since membranes, and presumably their pores, carry a surface charge because of their protein structure. Moreover, when ionization of solutes occurs, intraluminal pH will often influence the degree of ionization. In turn, pH can influence the chemical state and physical dimensions of the solute particles. For example, weak acids and bases ionize in accord with the ambient pH. Non-ionized molecules may be relatively lipid-soluble. Their ions much more water-soluble. Permeation of membranes by many drugs is affected by these principles. That such a model is of value in describing the passive permeation of the water phase through a biologic membrane in no way implies that the intestinal mucosa consists of a lipid barrier evenly studded with rectilinear holes. The model does not assume an even distribution of pores, and the specialized structure of the epithelial layer does not make this likely. Finally, the permeation of aqueous solute of large molecular size, for which no pores apparently exist, can only be explained on the basis of some specialized membrane function, possibly a carrier protein dissolved within the membrane.